The universe, as we know it, wasn't always filled with stars and galaxies. It began with the Big Bang, an event of unimaginable energy and heat. In the first few minutes after this cosmic explosion, the universe was a hot, dense soup of elementary particles. This period, known as Primordial Nucleosynthesis, is crucial to our understanding of the cosmos. It's the era when the lightest elements, the building blocks of everything we see, were forged. Imagine a universe so young that stars and galaxies were but a distant dream. The temperature was so high that atoms couldn't even exist. Yet, within this chaotic cauldron, the seeds of our universe were sown. This is the story of primordial nucleosynthesis, the era when the universe first created elements. This process is a cornerstone of modern cosmology. It explains the abundance of light elements like hydrogen and helium, which still dominate the universe today. Understanding primordial nucleosynthesis allows us to trace the universe's evolution from its earliest moments to the complex structures we observe billions of years later. The study of primordial nucleosynthesis is a testament to the power of physics. Using our understanding of nuclear reactions and the conditions of the early universe, we can accurately predict the amounts of these light elements. This predictive power makes primordial nucleosynthesis a remarkable example of how science can illuminate the distant past. To understand primordial nucleosynthesis, we need to rewind the cosmic clock to a fraction of a second after the Big Bang. At this moment, the universe was an unimaginably hot and dense sea of energy. As the universe expanded, it cooled, and this cooling was crucial for the formation of matter as we know it. The early universe, although extremely hot, can be thought of as a cooling oven. As the universe expanded, its energy was spread out over an increasingly large volume. This expansion led to a drop in temperature, much like how a hot oven cools down as heat escapes into the surrounding kitchen. This cooling process was not uniform. There were tiny quantum fluctuations in the early universe that resulted in minuscule variations in energy density. These fluctuations, although seemingly insignificant, would later play a crucial role in the formation of the large-scale structures of the universe, like galaxies and galaxy clusters. As the universe cooled, a pivotal moment arrived when the temperature dropped to about 1 billion degrees Celsius. This marked a critical threshold. The universe was now cool enough for quarks, the building blocks of protons and neutrons, to combine and form these composite particles. This transition, from a quark-gluon plasma to a universe filled with protons and neutrons, set the stage for primordial nucleosynthesis. Imagine a dance floor initially too crowded for couples to form. As the crowd thinned, dancers could finally pair up. Similarly, as the universe cooled, quarks, previously moving too energetically to bind, could now combine to form protons and neutrons. This marked a turning point in the universe's evolution. The formation of protons and neutrons was not the end of the story. The universe was still a very active place, with these particles constantly colliding and interacting. The energy of these collisions was high enough to initiate nuclear reactions, leading to the formation of the first atomic nuclei. This is where the story of primordial nucleosynthesis truly begins. The first element to form in the early universe was hydrogen, the simplest of all elements, consisting of just one proton and one electron. As the universe continued to cool, protons and neutrons began to stick together, forming the nucleus of deuterium, a heavier isotope of hydrogen. Deuterium, with one proton and one neutron, played a crucial role in the subsequent formation of helium. The formation of helium was a two-step process. First, two deuterium nuclei collided, producing a helium-3 nucleus which consists of two protons and one neutron. Then, two helium-3 nuclei collided, resulting in the formation of a stable helium-4 nucleus, containing two protons and two neutrons, and releasing two protons in the process. These reactions, occurring in the first few minutes of the universe's existence, were responsible for the initial abundance of hydrogen and helium. The ratio of hydrogen to helium, predicted by the theory of primordial nucleosynthesis, matches remarkably well with the observed ratios in the universe today, providing strong evidence in support of the Big Bang model. Section 5. The Dance of Protons and Neutrons. The relative abundances of hydrogen and helium in the early universe were determined by a delicate dance between protons and neutrons. Initially, these particles existed in roughly equal numbers. However, free neutrons are inherently unstable and decay into protons with a half-life of about 10 minutes. As the universe expanded and cooled, the reaction rates governing the conversion between protons and neutrons slowed down. This meant that neutrons were decaying into protons faster than they could be replenished through interactions with other particles. Consequently, the universe ended up with more protons than neutrons. This imbalance in the proton-to-neutron ratio had a profound impact on the outcome of primordial nucleosynthesis. Since helium nuclei contain equal numbers of protons and neutrons, the limited supply of neutrons placed a ceiling on the amount of helium that could be produced. This explains why the universe today is predominantly composed of hydrogen, the element requiring only protons for its nucleus. Section 6. A helium-dominated universe. The universe, after the first few minutes of its existence, was primarily composed of hydrogen and helium. The conditions weren't right for the formation of heavier elements. The universe had cooled too much for further nuclear fusion to occur efficiently. The window for primordial nucleosynthesis had closed. The predominance of hydrogen and helium in the early universe has had a profound impact on the evolution of stars and galaxies. Hydrogen, the most abundant element, is the fuel for stars. Helium, the second most abundant element, plays a crucial role in stellar evolution and the production of heavier elements within stars. The abundance of helium in the universe is a key piece of evidence supporting the Big Bang theory. The predicted amount of helium produced during primordial nucleosynthesis aligns incredibly well with observations of the oldest stars and galaxies, further solidifying our understanding of the universe's early history. Section 7. Deuterium, a cosmic witness. While hydrogen and helium are the most abundant products of primordial nucleosynthesis, a tiny amount of lithium was also produced. Lithium, the third lightest element, formed through the fusion of helium-4 and tritium, another isotope of hydrogen. The abundance of lithium, although small, provides valuable insights into the conditions of the early universe. Deuterium, the heavier isotope of hydrogen, plays a crucial role as a cosmic witness to the events of primordial nucleosynthesis. Its abundance is sensitive to the density of baryons, which are protons and neutrons in the early universe. By measuring the amount of deuterium in the universe today, cosmologists can estimate the baryon density, a key parameter in cosmological models. The observed abundance of deuterium indicates that the early universe was not dense enough to form significant amounts of heavier elements beyond helium. This finding supports the idea that most of the heavier elements we observe today were forged much later in the fiery hearts of stars and during supernova explosions. Section 8. Echoes from the Big Bang. Primordial nucleosynthesis left behind an indelible mark on the universe in the form of the cosmic microwave background, or CMB radiation. This faint afterglow of the Big Bang provides a snapshot of the universe when it was just 380,000 years old. The CMB carries information about the temperature and density fluctuations in the early universe. By studying the subtle variations in the temperature and polarization of the CMB, cosmologists can infer the conditions that prevailed during primordial nucleosynthesis. These observations have allowed us to precisely measure the amount of light elements produced in the early universe, confirming the predictions of the Big Bang model with remarkable accuracy. The CMB is a treasure trove of information about the early universe. Its discovery revolutionized our understanding of cosmology and provided compelling evidence in support of the Big Bang theory. The study of the CMB continues to be an active area of research, providing increasingly precise measurements of cosmological parameters and shedding light on the universe's earliest moments. Section 9. Looking back in time. Primordial nucleosynthesis provides a remarkable window into the first few minutes of the universe's existence. By studying the abundance of light elements and the cosmic microwave background radiation, we can piece together a detailed picture of the universe's infancy. These observations confirm the predictions of the Big Bang model with astonishing accuracy, solidifying our understanding of the universe's early evolution. The study of primordial nucleosynthesis is a testament to the power of human ingenuity. Using the laws of physics and sophisticated observational tools, we can probe the distant past and unravel the secrets of the universe's origin. The success of primordial nucleosynthesis as a scientific theory highlights the remarkable unity and elegance of the universe, where the same physical laws govern both the smallest atomic nuclei and the largest cosmic structures. As we continue to explore the cosmos, primordial nucleosynthesis serves as a reminder of the profound connections between the microcosm and the macrocosm. It reminds us that we are all products of the stars, forged from the remnants of the Big Bang, and that the quest to understand the universe is a journey of self-discovery.